So terminating decimals means it will stop after certain decimal point. So if any number is divisible by 2, that means the number is even. So this implies P is even. The number in the form of P by Q is said to be a rational number and it is denoted by Q. Remember, square root of positive integer is a rational number because we do not define any square root for negative numbers. Hello everyone, a warm welcome to one and all. This is Ashruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. In this session, we are going to study about the other types of number: rational, irrational, real and complex number. So first, rational number. We know that any number in the form of P by Q. So P and Q are integers and Q not equal to 0. So we know that the denominator can never be 0. So the number in the form of P by Q is said to be a rational number and it is denoted by Q. Now, here every integer is a rational number. So that means if I consider 1 can be written in the form of 1 by 1. If I consider 0 can also be written in the form of 0 by 1. If I consider any negative number, -7, then -7 can also be written in the form of -7 by 1. So every integer can be expressed in the form of a rational number provided denominator will be equal to 1 there. And the next thing is 0 is a rational number since we can write it in the form of P by Q, where P and Q are integer and not equal to 0. And square root of a positive integer is a perfect square, is a rational number. Remember, square root of positive integer is a rational number because we do not define any square root for negative numbers. So we define square root for positive numbers here, then it is said to be a rational number. For instance, square root of 16 is 4, square root of 25 is 5. So if we use the concept of plus or minus 5, then plus 5 can be written as 5 by 1 and minus 5 can be written as minus 5 by 1. Hence, a square root of a positive number is also a rational number. Next, terminating and recurring decimals. So what is the relation with the rational number? Now, all rational number when expressed in the decimal form are either terminating decimals or recurring decimal. So terminating decimals means it will stop after certain decimal point. Recurring means it is non-terminating or it will be revised again. That means, for example, if you consider 1 by 3 in the form of P by Q, the decimal form of 1 by 3 is 0.33333, etc. So it will be recurring until the infinite number of terms. So here recurring decimal means a decimal representation in which all the digits after a certain stage are repeated is called as recurring decimal. And mixed recurring decimal. Sometimes we might get an example in such a way that we might get 0.125, 125, 125, etc. So this is an example of mixed recurring decimal. So that means few digits repeats after being repeated once again. So a decimal in which some digits after the decimal point is not repeated and then some digits are repeated is called as mixed recurring decimal. Now, let us take an example of rational number and let us express them in a decimal form. So, we have 3 by 4 here. So, that means we need to divide 3 by 4. So, we will put 0 point here. So, 0 we will get. So, 4 sevens are 28, 2 remainder. Again, we can take 0, 4 fives are 20. So, therefore, the decimal form of 3 by 4 is 0.75. Next one. 8 divided by 125. So, we need to divide 8 by 125. So, we can't take here 0.0. We'll take one more 0, put 0 here. So, we have 6 750. So, we are left with 50. Again 0. So, we can take 4 so 500. So, therefore, the decimal expansion of this is 0.064. Next question. The next thing is we have a note. Any number in the form of P by Q is said to be rational number such that the prime factorization of Q is of the form 2 power n into 5 power m. Then decimal expansion of P by Q terminates. Suppose they have given a number P by Q. Now, if q can be expressed in the form of 2 power n into 5 power n. For example, if you have given an example like 3 by 10, remember 10 can be written as 2 into 5, 2 power 1 into 5 power 1. So, this is of the form 2 power n into 5 power m. In such a case, we can say the decimal expansion of the rational number terminate. So, without actual division, just by assigning q in the form of 2 power m into 5 power n, we can express whether the decimal expansion is terminating or recurring. For instance, let me take an example of 120 by 7. Now, 7 is 1 into 7. It is not in the form of 2 power n into 5 power n. In such a case, we can directly say the decimal expansion does not terminate. Now, if p by q is a rational number such that prime factorization of q is not in the form of 2 power n into 5 power m, then decimal expansion p by q is called as non-terminating decimal expansion. Now, let's take an example here. Without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or non-terminating repeating decimal expansion. So, non-terminating means it has to be a recurring decimal expansion. So, note that a rational number is either having always the decimal expansion which is terminating or non-terminating recurring decimal expansion. Now, let's see here 17 divided by 3125. So, let us divide this 3125 by 5. So, we have 5 6 are 30, 1 carry, 5 2s are 10, 1 carry, 5 5s are 25. Next, 5 1s are 5, 5 2s are 10, 5 5s are. Next, 5 2s are 10, 5 5s are. So, 5 5. So, clearly the q 3125 is 2 power 0 into 5 power 5. So, this is of the form 2 power n into 5 power m. So, clearly we can conclude the decimal expansion of this rational number is terminating. Next, 139 divided by 2 cube into 5 square. In the question itself, the denominator q is already in the form of 2 power n into 5 power m. So, therefore, clearly the decimal expansion of this rational number terminates. So, you can also take an example or non-example. For example, if it is 77 by 210 here, let us see the prime factorization of 210. 2 ones are, next 2 zeros are, 2 5s are, next 5 2s are 10, 5 ones are, next 3 into 7. So, here 210 is equal to 2 power 1 into 5 power 1 into 3 power 1 into 7 power 1. So, clearly this is not in the form of 2 power n into 5 power n. It should be only in the form of 2 power m into 5 power n, but we have 3 and 7 also. So, clearly this decimal expansion is non-terminating decimal expansion. Next, we look upon the irrational number. So, the numbers which are not rational are called as irrational number. So, it cannot be put in the form of p by q here. So, for example, root 2, root 3, root 7 are called as irrational number. Note here, a negative of an irrational number is an irrational number. For example, we have taken an example of root 2. If we take negative of root 2, that is minus root 2, minus root 3, minus root 7, they are also an irrational number. Sum of rational and irrational number is always an irrational number. Let us take an example of a rational number. Let it be 3, and let me take an example of root 5. Now, this is rational number and this is an irrational number. So, sum of a rational and irrational is always irrational. So, it can never be a rational number. Product of non-zero rational number and an irrational number is irrational. For instance, if I multiply 1 by 2 with root 2, then obviously it is root 2 by 2 again, or on simplification, we can write this as 1 by root 2. So, this is also an example for irrational, and here the product of rational and irrational will be irrational number. Prove that root 2 is an irrational number. Now, let us assume that root 2 be rational number. Now, if any number is in the form of rational number, then it can be expressed in the form of P by Q. So, therefore, root 2 is equal to P by Q, where P and Q belongs to the set of integers Q not equal to 0. And also, P by Q will be always in its simplest form. That means P and Q are co-prime. So what do you mean by co-prime? So the HCF of two numbers is equal to 1. That means P and Q will be in the simplest form where P and Q are prime numbers and their HCF is equal to 1. So here this means HCF of P and Q is equal to 1. So they are co-prime numbers means the HCF of two numbers is 1. Now observe this condition. We have root 2 is equal to P by Q here. I'll shift Q to the left hand side. Then root 2Q is equal to P. Let's square on both sides. 2Q square is equal to P square. So when you multiply Q square to 2, you are getting P square. So that means 2 divides P square. When we say 2 divides P square, then 2 divides P. So if any number is divisible by 2, that means the number is even. So this implies P is even. Now, if P is even, then it should be a multiple of 2. So therefore, let me consider P is equal to some 2k. So let P is equal to some 2k. If P is an even number, then it should be the product of 2, where k may be any integer. Now let us square on both sides. We have P square is equal to 4 into K square. Now using this condition, instead of P square, I can write 2 into Q square. So 2 into Q square is equal to 4 into K square. Cancelling this, we'll get Q square is equal to 2 into K square. So we can clearly see Q square is a product of 2. That means 2 into Q square. So that implies 2 divides Q square. So when 2 divides Q square, that can also divide Q. If Q is divisible by 2, that implies Q is even. So here we got P is even and here we got Q is even. So that implies HCF of P and Q is even. That is 2. Because 2 divides P, 2 divides Q, that implies HCF of P and Q should be equal to 2. But according to my assumption, P and Q are co-prime numbers, which means the HCF of P and Q is equal to 1. So here I am getting the statement that HCF of P and Q is 2. So therefore, it is wrong, which is wrong. So that means the given statement contradicts our assumption that root 2 is a rational number. So here we can conclude our assumption is wrong. So therefore, root 2 is an irrational number. So to prove any irrational number, so we can take that number as a rational number. So this process of proving this result is called as contradictory method. So we will take the contradiction of the statement and show that our assumption is wrong and hence the given statement is true. So we can say here root 2 is rational. Express root 2 in the form of rational number. We will get two numbers which is even and hence their HCF is 2. But HCF of P and Q is 1. Hence our assumption is wrong. So clearly we can say our assumption is wrong. Therefore root 2 is an irrational number. Let's take one more example. Prove that 2 plus root 3 is rational number. Now let us assume 2 plus root 3 as a rational number. So here also P and Q belongs to the set Z and Q not equal to 0. Now let me shift 2 to the right hand side. Then we get root 3 is equal to P by Q minus 2. So root 3 is an irrational number and P by Q is rational number and 2 is a rational number. So when you subtract two rational number, the result is rational number. But root 3 is irrational. Nowhere a rational number and irrational number can be equal. So we clearly know that the number which is not rational is an irrational, or a number which is irrational cannot be rational. So therefore clearly we can say irrational number is not equal to rational number. So that means my assumption taking 2 plus root 3 as a rational number is wrong. So clearly we can say 2 plus root 3 is an irrational number. We also studied under the note that the sum of rational and an irrational number is irrational number, and hence 2 plus root 3 is an irrational number. Next we study surds. So what are surds? An irrational root of a rational number is called a surd. So for example, root 2, root 5 plus 3. So these are all example for a surd. Next, transcendental number, an irrational number which is not a surd, that means pi. So here pi is nothing but 22 by 7. Even though it is in the form of P by Q, the decimal expansion of 22 by 7 never terminates, and not even it contains a recurring decimal expansion. So therefore, the number which is neither terminating nor have a recurring decimal expansion is nothing but an irrational number. And under an irrational number, pi is called as transcendental number, whereas root 2, root 5 plus 3 are called as surds. Next we come across the type of number system which is the real number system. So real number is nothing but the union of all rational number as well as irrational numbers. So rational numbers and irrational numbers taken together are said to be form a set of real number, and the set of real number is always denoted by R. So a real number is either rational or irrational. So it is always the union of rational, and we know that the complement of rational is irrational. That's why we have represented it in the form of Q dash. So the union of rational and irrational number is the real number. So real number is the biggest system of numbers R. So here this is a rational number, and out of the circle this is the set which contains irrational number. Under rational number, we may have natural numbers, whole numbers, integers, prime numbers, odd numbers, even numbers, etc. So this is the set of rational number, and out of the circle it clearly represents an irrational number. So the complete set which includes rational as well as the irrational number are called as real numbers. Now, every real number can be represented by a unique point on the real number called real number line, and conversely. So we know that we already represented some natural numbers, integers on the number line. So if we represent using this number line, as we move from left to right, the value of the numbers increases. So suppose if I consider this as minus 1, 2, 3. So we will always plot the point minus 2, minus 1, 0, 1, 2, 3. So we know that real numbers are nothing but they will be always having a decimal expansion. So they can be between in any integers. So there are infinite number of real numbers between any two integers. So if I consider an integer 1 and 2, so clearly X is a real number which may take any values between 1 and 2, which always represents a real number. Next is the complex number. The numbers which are not real numbers are said to be complex number, and here the complex number is always represented in the form of a plus ib, where a and b are real number. And we have here I. So I is nothing but the irrational root of negative number. So I already told you we always find the square root of positive numbers. So here we have a square root of a negative number. So in case if you get a square root of negative number, it is not a real number. It is considered under the complex number and it is denoted by C. So here any number in the form of a plus ib, where a is a real number, b is real number, but a plus ib is a complex number. And clearly the value of I is root of -1, and when you square, I square is equal to -1. So this type of number which includes I is called as complex numbers. And when we write a plus ib form, here a is called the real part and b is called the imaginary part of complex number. Any number with I is called as the imaginary part of complex number. Now here we have taken an example, 1 plus 6i. 1 is the real part, 6 is the imaginary part. 3 minus 4i. 3 is the real part, minus 4 is the imaginary part. Root 2 plus root 3i. 2 is the real part, root 3 is the imaginary part of the complex numbers. Next we come across the equality of a complex number. Now suppose we have two complex numbers, say a plus ib and c plus id are two complex number. Then a plus ib is equal to c plus id if and only if a is equal to c and b is equal to d, which means two complex number are said to be equal if the real parts are equal and similarly if their imaginary parts are equal. For example, a plus ib is equal to 4 plus 3i, which means a is equal to 4, b is equal to 3. Similarly, a plus ib is equal to 0 plus 0i, which means a is equal to 0, b is equal to 0. So clearly, when their respective real parts as well as imaginary parts are equal, we say the two complex numbers are equal. Next, we have few properties of complex number. So we can also study the algebra of complex number. So that means we can add two complex number. For example, 2 plus 3i, 1 minus I. So if we want to add this, then we always add real number or real parts to real parts and imaginary parts to imaginary part. So clearly you can see here 2 plus 1 is 3. 3i minus I is minus 2i. So this is the sum. If I take the same example, 2 plus 3i minus 1 minus I. So I'm subtracting two complex numbers here. So which is 2 plus 3i minus 1 plus I. So which is 2 minus 1, 1. 3i plus I is 4i. So here I'm subtracting two complex numbers. Next, we come across the product of two complex number. So let's take an example of the same, 2 plus 3i into 1 plus I. So we can use the binomial product here also. So multiply real part to the whole complex number and then plus 3i to 1 plus I. So which we have already studied the binomial product in algebra. We can use the same strategy here. So 2 ones are 2 plus 2 into I, 2i. 3i into 1, 3i, plus 3i into I becomes 3i square. Remember the value of I square is always equal to minus 1. So if you substitute here minus 1, then this is 3 into minus 1, which is equal to minus 3. And here we have 2i plus 3i, which is 5i and 2. So 2 plus 5i minus 3. 2 minus 3 is minus 1 plus 5i. Again, this is in the form of a plus ib. So here value of a is minus 1, which is the real part, and value of b is 5, which is the imaginary part. In the same way, we can also convert the division of two complex number in the form of a plus ib, which again represents one more complex number. Apart from this, we have two important concepts under the complex number. One is the conjugate of the complex number and the other is modulus of the complex number. Now suppose let z is equal to a plus ib be the complex number. Then the conjugate is always denoted by z bar. So which is nothing but conjugate of a complex number. So the conjugate of a complex number is always in the form of a minus ib. Now for example, if 5 plus 3i is the complex number, then the conjugate of complex number is 5 minus 3i. Now if we have root 3i minus 1 as the complex number, then minus root 3i minus 1 is its conjugate. Remember, you always take the opposite sign in the imaginary part here, not to the real part. So the real parts remains the same. So conjugate of a complex number means you change the sign of the imaginary part, plus to minus or minus to plus. The next thing is the modulus of the complex number. So modulus of the complex number is denoted by modulus z, which means it's a square root of sum of square of the real part as well as the imaginary part. It is a square root of your a square plus b square. If I take an example of 5 plus 3i, then modulus of 5 plus 3i is nothing but square root of 5 square plus 3 square. So which is 25 plus 9, which is equal to root 34. So this is the modulus of the complex number. Next we have write the real and imaginary parts of the following complex number. The first one is 3 plus 5i. Clearly, real part a plus ib is equal to 3 plus 5i. So the real part a is equal to 3 and the imaginary part b is equal to 5. Next, 1 plus I into minus 2 plus 3i. So here we need to product these two complex number and again the resultant will be again the complex number. So let's multiply 1 with minus 2 plus 3i and plus I with minus 2 plus 3i using the concept of binomial product. So minus 2 plus 3i minus 2i plus 3i square. Again I square is nothing but minus 1. So 3 into minus 1 is minus 3. 3i minus 2i is I and here we are left with minus 2. So now this is equal to minus 2 minus 3 is minus 5 plus I. So if nothing is there, the value is nothing but 1. So therefore the real part is minus 5 and the imaginary part is 1. Remember, the number 0 can be represented in the form of 0 plus 0 into I. Here I is not 0. I is always equal to root of minus 1. Since the real as well as the imaginary part is 0. Since b is 0, the imaginary part becomes 0 and hence the real part. Any other numbers, any real numbers can also be represented in the form of complex number where its imaginary parts become 0. For instance, if I have to write 2, 2 is already a real number but it can be expressed in the form of complex number, which means I can write 2 plus 0 into I. Remember here the value of b is always 0. So therefore it exists only the real part but imaginary part is 0 here. Next question is 1 divided by 4 plus 3i. So we have a complex number in the denominator. So let us use the concept of rationalizing the denominator. So I'll multiply the conjugate of 4 plus 3i. So what is the conjugate of 4 plus 3i? It is 4 minus 3i. Now let me multiply this. 4 minus 3i into 1 is 4 minus 3i. And denominator, this is in the form of a plus b, a minus b, which can be written as a square minus b square. Now here we have 4 minus 3i divided by 4 square is 16 minus 3 square is 9. I square is minus 1. So minus 1 into minus 9 becomes plus 9. So this is 4 minus 3i divided by 25. Now separate the denominators along with the numerators. So 4 by 25 minus 3 by 25i. So here the real part a is 4 by 25 and the imaginary part b is minus 3 by 25. So to conclude this, if suppose we have any two complex number z1 and z2, we can define the sum of two complex number, we can define the difference of two complex number as well as the product of complex number as well as the quotient of complex number provided Z2 is not equal to 0. Again, all these form is once again the complex number which is in the form of A plus IB. So in this chapter, we have studied different type of number system and HCF, LCM of numbers, and we have studied about the complex number. So this is all about the chapter number theory. I'll meet you in the next session with the new chapter. Until then, keep watching, keep learning, and keep exploring. Thank you.